Okay, so the third application that we're going to be looking at is that of using derivative to find stationary points of graphs. And this then extends to an application if the graph represents quantities, being able to maximise and minimise various quantities using derivative. But for this exercise, we'll just look at, given a function, finding coordinates of stationary points. And then down the track, we'll look at examples where that might be surrounded by context. So stationary points are points where the gradient is 0. Okay, so that is when your derivative is equal to 0. And there are three types of stationary points. Turning points, which could be local minimum or local maximum, or stationary points of inflection. Now, we're actually missing a diagram here in this table, so let's take the opportunity to sort of draw it in. Let's talk about the ones we've got here, and then we'll draw in the third one. So in a local minimum point, so if your original function is the red curve, let's say it looks like a parabola, and we have a local minimum at the point a, f of a, then we know that when we draw the derivative function for that, the derivative function will be a straight line that goes through the point a0. It has an x-intercept at the point a0, and that's because when x equals a, gradient is 0. Okay, so the key idea in thinking about how to understand that we have a local minimum is that at the stationary point, so there is a stationary point when x equals a. When x is less than a, the gradient will be less than 0, and when the gradient will be negative, and when x is bigger than a, the gradient will be bigger than, now sorry, that's a typo there in that table, can we fix that? The gradient will be bigger than 0, okay? So you go from having negative gradient, 0 gradient, positive gradient, okay? When you have a local maximum, the opposite happens. You go from having positive gradient when x is less than a, 0 gradient at a, and then negative gradient when x is bigger than a. Okay. Stationary point of inflection, so we've got one drawn here, an increasing function. So we have a stationary point of inflection, the red graph. If we were to draw its derivative, so let's imagine the red graph is a cubic, the derivative in that case would be a quadratic. And we would have this situation where we have a positive gradient before the x equals a, 0 gradient at x equals a, and still positive gradient after x equals a. So we get this sort of graph. Now let's say we had, let's say we had instead, let's say that's our x-axis. Let's draw in, let's say we've got a stationary point of inflection that goes this way. Then again, if the original functions are quadratic, let's say that's the point a, f at a, this is y equals f of x. We know when x equals a, the gradient, the derivative will equal 0. And this time we know that when x is, when x is less than a, we have negative gradient. And when x is bigger than a, we still have negative gradient. So our graph would be our derivative graph would be down here. So again, thinking about what happens, what's the sign of the gradient either side of the stationary point is what's key. This is called a sign diagram. We'll talk more about that. So for example, when x is a, the gradient, so looking at the left-hand diagram here, when x is a, the gradient is 0. When x is less than a, the gradient is bigger than 0, positive. At a, it's 0, and when x is bigger than a, it is positive again. In the second stationary point, we would have negative gradient, followed by 0 gradient, followed by negative gradient. So being able to look at the sign of the gradient either side of the point of 0 gradient will tell us about the nature of the stationary point. Is it a local minimum point? Is it a local maximum point? Or is it a stationary point of inflection? It's possible to also use the second derivative to justify the nature of stationary points. It's something that the specialist math students will be more familiar with. I'm personally not that keen on delving into the realm of second derivative. I think it's much more explicit and much less open to having to remember rules if you think about the sign of the gradient either side, and I'll show you the way that you need to set that up in order to justify the nature of your stationary point. Okay, let's have a look at some examples. So if we need to determine or justify the nature of a stationary point, you must do so using a sign diagram, which is going to be my preference. I'm going to show you how to use the sign diagram, which considers the sign of the gradient either side of the stationary point, or you use the second derivative and you draw a clear conclusion based on understanding of second derivative. I'm going to talk about the first example. So So for example, if we're to find the location and determine the nature of the stationary points of this particular function, we could use the following process. And we're talking about functions where if it's a simple quadratic function and you can draw a rough sketch to say, it's clearly a local minimum at this stationary point, that's fine. But we're talking about examples of functions where we might not know what the graph actually looks like, and so we might need to therefore rely on other methods to determine, okay, I know it's got two stationary points, but what's actually happening at those stationary points? So if my function is x e to the negative x, we're going to find the derivative first of all, which would require quotient rule. So that's done here. And then for the stationary point, we need to know where does the derivative equal 0. So this is really key. Okay, derivative equals 0. Even if you've got your CAS and it's going to do it for you, you're still going to write down that line that says I'm solving f dash x equal to 0, and then straight away get to the answer. So we can do this by hand. We can factor out our e to the negative x, which gives us e to the negative x times 1 minus x, and then we're using the null factor law, which says, well, either that thing equals 0 or that thing equals 0. Okay. Now, e to the negative x can't ever equal 0. Exponential function reflected in the y-axis looks like this. It doesn't ever equal 0. So that's not going to give you a solution. So that's what this says here. E to the negative x cannot equal 0, which means that we're just looking at 1 minus x equals 0, and so x equals 1. So there is a stationary point when x equals 1, and we can find the coordinates of that stationary point by substituting 1 back into our original function, not back into the derivative. Subbing it into the derivative will give us 0, because that's how we found it. So subbing into the original function to find the y value, and when we do that, f of 1 is e to the negative 1 or 1 on e. And so we know there's a stationary point at 1, 1 on e. Now, that doesn't tell you, all that tells you is at that point there's 0 gradient. It doesn't tell you whether that's a local minimum point, a local maximum point, whether that's a stationary point, whether that's a point of inflection. And so therefore we then need to use either our sign diagram or our second derivative. As I said, my preference is sign diagram to determine the nature of the stationary point. Okay, so we set up a little table like this, and you literally draw this, okay? So you've got your x values. You're going to start with the middle. So what we've learnt from up here, when x equals 1, the gradient is 0, and so therefore that's where we have a stationary point. The slope of the graph at that point is flat. Okay, and then we're going to think about a point either side of that point. Now you can pick any number here, a number that's less than 1, a number that's bigger than 2. Usually you would try to stick quite close to your actual value of the turning point, and you would often do that particularly if the graph has more than one stationary point, because you don't want to run the risk of, okay, let's say it's got a stationary point when x equals 1, but let's say you test the gradient here, that's fine, but over here, okay, what it's missed is you've gone past the second stationary point, and therefore you're not looking at the behaviour of that stationary point when x equals 1. So you want to pick values either side of 1, staying as close to 1 as you can. But in this instance, we know there's only one stationary point, so we could pick any old points either side, and it wouldn't really matter. I'm just going to go with 0 and 2, one either side. They don't need to be symmetrically either side of the stationary point, okay, either, so pick points that are convenient. When I sub x equals 0 into my derivative, so we want to know what is the gradient when x equals 0. So it goes into the derivative, okay? When I put it into the derivative, I get e to the 0 minus 0 times e to the 0. So that is 1 minus 0, which is 1, okay? And I also take my x equals 2 and I sub that into the derivative, and when I do that, I'm going to get e to the negative 2 minus 2 times e to the negative 2, which is negative e to the negative 2, which is negative 1 on e squared. Okay, and that's how I've got these values in here. Alright, so then I have draw interpretation. So when x equals 0, the gradient is 1, which means my graph is sloping up. It's positive. Okay, when x equals 2, the gradient is negative 1 on e squared. Remember, e is about 3, so it's about negative 1/9. It's negative. It's not symmetric, it doesn't matter. The fact that you've got positive gradient to the left of the stationary point, 0 gradient at the stationary point, negative gradient after the stationary point, tells you that you have a local maximum when x equals 1. Okay, you must use the justification method to show it. You can't just write positive and negative here. You have to actually calculate values for this specific function that show that that's a positive value and that's a negative value. Okay, so it's not enough just to, again, it's a bit like the examples where we talked about composite functions back earlier on in chapter 1. It's not enough to just say, oh yeah, this is defined because the domain of this is a subset of the range of this, or whatever it might be. you need to actually state what those relevant domains and ranges are to justify that you're not just parroting a statement out of a textbook that anyone can do, you're actually relating it to the specific example. Now, if you use the second derivative, so you differentiate the derivative to get the second derivative, which is, in this case a little bit complex because you have to do product rule again, and the tidying up takes a little bit. And then you will look at the value of the second derivative at the stationary point. Okay, and in this case, the second derivative is negative, and a negative second derivative means that we have a local maximum. As I said, that requires you to remember those rules. Personally, I prefer the sign diagram, and I will complete the examples using a sign diagram. So, derivative equal to 0, find the coordinates of the point. You know there's a stationary point there, then determine what type of stationary point you have using a sign diagram or the second derivative. Okay, let's have a look at some examples. So find the coordinates of all the stationary points on the graph of y equals x squared times e to the negative 2x and state their nature. Okay, so that is the type of stationary point. Okay, so let's first of all focus on finding where the stationary point or points are. So we're going to need our derivative. So dy dx is going to be, we need product rule here. So derivative of x squared is 2x times e to the negative 2x, and then plus, leave the x squared as it is. Derivative of e to the negative 2x is negative 2e to the negative 2x. Okay, so we've got 2x e to the negative 2x minus 2x squared e to the negative 2x. So let's factorise because we're going to need to solve it, and this is where that algebra is important because solving this equal to 0, we need to actually factorise this. So common factors in these two terms, we've got 2 in common, we've got an x in common, and we've got e to the negative 2x in common. When we take that out, we get left with 1 in the first term and x in the second term. Okay, so we now want to solve our derivative equal to 0 for the stationary point, so we're solving this equation. So this means null factor law, either 2x equals 0, which means x equals 0, or e to the negative 2x equals 0, which is not possible, or 1 minus x equals 0, which means x equals 1. Okay, so we've got two stationary points when x equals 0 and x equals 1. We want the coordinates, so let's do that. Okay, so when x equals 0, so we're going to go into we want y, not dy dx, so we're substituting back into the original equation. Okay, so when x equals 0, y is going to be 0 squared times e to the 0, so that is 0 times 1, which is 0. So our first stationary point has coordinates 0, 0. And when x equals 1, y equals 1 squared times e to the negative 2, so it's just e to the negative 2. So we have 1 e to the negative 2, or 1 on e squared. Now it's not enough to say, oh well that y value is higher than that one, and so therefore that's a max and that's a min, because you could have a graph with a min and then a stationary point of inflection. You could have a point of inflection and then a minimum. You could have a maximum and then a point of inflection. You could have all sorts of things. So you can't just, it's not about comparing y value, you need to compare gradient to determine the nature. Okay, so we're going to use a sign diagram to find the nature, and we don't need two separate sign diagrams here, it's just the one sign diagram. So we want to think about our x values. We know we have a stationary point when x equals 0, and we know we also have a stationary point when x equals 1. Okay, so I need to look at points either side of 0. So let's maybe say negative 1. Now I'm going to need to look at a point between 0 and 1 so that I can determine what's happening with the gradient between those two stationary points. So let's go with a half. Okay, and then we're going to need an x value after the second stationary point to see what's happening after that point. So maybe we go with 2. Okay, so we're going to focus on calculating the gradient. So we want dy dx at each of those x values. And then we want to make a, draw a conclusion based on what that means for the slope or the shape of the graph. Okay, so we know when x equals 0, dy dx is 0, that's a stationary point. We know when x equals 1, dy dx is 0, that's a stationary point. Okay, so let's think about negative 1. So where's our equation of derivative? Alright, so let's put negative 1 into here, or any of these versions of my derivative. Okay, So we're going to have, maybe I'll do this down here because it's going to get a bit ugly. So when x equals -1, our derivative is going to be -2e to the positive 2, 1 minus minus 1, so 1 plus 1. So that's going to be negative 4e squared. Okay, so that's clearly a negative value. E squared is positive. Remember, e is about 3. 3 squared is 9. Times -4 makes that negative 36-ish. Okay, so it's definitely negative. All right, when x is a half, let's think about the derivative. Okay. Sorry, it's not that one, it's this one. So dy dx will be, it's going to be 2 times a half, so I'm using this bottom line here. 2 times a half, so that's just 1. E to the -2 times a half, so e to the -1. And then we've got 1 minus a half, so that's going to be half. So we have half e to the -1, which is 1 on 2e. Okay, there's nothing negative there. It's small, but it's not negative, it's positive. Okay. Sorry, 1 on 2e. So we have a positive gradient. And then when x equals 2, dy dx is going to be 2 times 2, so that's 4. E to the -2 times 2, so e to the -4. And then it's times by 1 minus 2. So that's -1. So we get -4e to the -4, which is -4 on e to the power of 4. So the negative power is not making it negative, but the negative out the front is. So that's negative. Okay, so we do have a local minimum followed by a local maximum here. So let's draw our conclusion, finish off our question. So let's be clear what the question asks us for. Find the coordinates of all stationary points on the graph and state their nature. Okay, so what do we have? At the point 0, 0, we have a local minimum. Local minimum at 0, 0, and we have a local maximum at the point 1, 1 on e squared. So we've given the coordinates of the stationary points and stated their nature. There's our final answer there. Okay, example 2. Show that the graph has a local minimum at 3 on 2, 9 on 4. So first of all, we need to show that it has 0 gradient at that point. And then we need to show, if it's a local minimum, that we have negative gradient before that point and positive gradient after that point. Okay. All right, so we want dy dx. Again, remember, show that we have a local minimum at this point. Basically says, find the local minimum. Hint, it should be 3 on 2, 9 on 4. Okay, so dy dx is going to be, in this case, 2x minus 3. Okay, so we know derivative will, when we want stationary points, derivative equal to 0. So we get 2x equals 3, and so x equals 3 on 2. Okay, so that means that we definitely have 0 gradient at x equals 3 on 2. We then need to put that value back into our equation to show that the y value at that point is 9 on 4. 3 on 2 squared minus 3 times 3 on 2. So that is 9 on 4 minus 9 on 2. Sorry, there's an error in the question here. Sorry, that's my fault. It should be negative 9 on 4 in the question. So can you fix that? The point should actually be, show that there's a local minimum at 3 on 2, negative 9 on 4. My apologies. Okay, so we're in the process of showing that it's negative 9 on 4, not positive 9 on 4. So that's 9 on 4 minus 18 on 4, and so negative 9 on 4. Okay, so at this point, we know that we have a stationary point when x equals 3 on 2. At this point, we know that we have a stationary point at the point with coordinates 3 on 2, negative 9 on 4. So now we need to show that that stationary point is indeed a minimum stationary point. All right, so we want to think about x values either side of the stationary point. So 3 on 2 is 1.5, so we could go with 1 and 2. We want to know what is the derivative, and we want to know what that means for the shape of the graph or the slope. Okay, we know at x equals 3 on 2 the gradient is 0. That means we've got the stationary point there. Here's our derivative up here. So we're subbing x equals 1 into the derivative. So when x equals 1, we get 2 minus 3, so we get negative 1. When x equals 2, we get 4 minus 3, so we get positive 1. So we get negative gradient and then positive gradient. So at this point, therefore, what we've shown is we have a local minimum at the point 3 on 2, negative 9 on 4. Okay, so you need to show those three things: that there's 0 gradient at 3 on 2, that the y value is negative 9 on 4 when x equals 3 on 2, and that at that point you have a local minimum. Okay, example 3. The curve with equation y equals x squared plus ax minus 4 has a stationary point when x equals negative 1. Find a. Okay, so it tells us we have a stationary point. So stationary point when x equals negative 1 means that dy dx equals 0 when x is negative 1. Okay, all right, so let's find dy dx. So dy dx is going to be 2x plus a. Okay, so we know when x equals negative 1, dy dx will equal 0. So that means we have 0 equals 2 times negative 1 plus a, and so 0 equals negative 2 plus a, and so a equals 2. Okay, example 4. The graph of this generic cubic function, ax cubed plus bx squared plus cx plus d, touches the line 4x plus y equals 12 at the point 1, 8, and has a stationary point at 0, 3. Find the values of a, b, c, and d. Okay, with 4 unknowns, we're going to need 4 pieces of information. So we need to interpret and need to work out what these 4 bits of information are in this case. All right, the first one, the most useful one, well actually the first most useful 2 bits of information are the fact that it goes through these 2 points. So we know that f of 1 is equal to 8, and we know that f of 0 is equal to 3. Okay, then we're actually told about the gradient at each of those points. So we know that the curve, the cubic curve, touches the line. Okay, so that means it's tangent to the line. So that means it has the same gradient as the line at that point. So this line, if we make y the subject, is negative 4x plus 12. So we know that the gradient at the point 1, 8 is going to be negative 4. So f dash at 1 is negative 4. And we know there's a stationary point at 0, 3, which means the gradient at 0 is going to be 0. So there's our 4 equations that we're going to need to solve simultaneously to find a, b, c, and d. Now, 4 simultaneous equations in 4 unknowns is not, you wouldn't be doing this by hand. This is a CAS question. And I want to talk about some things you need to be careful of in using your CAS to solve this. It's a bit fiddly to enter this in, but it's important that you kind of practice this. Okay, so the first thing we need to do is define our function. We've done this before. We've done problems like this before. So menu 1, 1, we're going to define f of x. And we need to be careful when we define this function that it is a times x cubed. If you don't explicitly write the multiplication, it will assume you mean some unknown called x cubed. So you must tell it you mean a times x cubed. That's the first place you'll go wrong here. Plus b times x squared plus c times x plus d. Okay, we define our general function. Then we're going to want to solve 4 simultaneous equations. Menu 3, 7, 1, 4 equations, and the unknowns in those equations are a, b, c, and d. Okay, so we set up our simultaneous equations template. The first 2 equations are really easy to enter in. F of 1 equals 8. Oops, sorry, lost the equal sign there. Equals 8. And the second equation, f of 0 equals 3. Great, they're easy. Now the second 2 equations, we want to talk about the derivative when x equals 1. Now I want to be clear about this notation. Let's talk about this using your CAS. So we know that when we use our CAS to find derivative, we're going to, it's going to be d dx of f of x. Okay, that will be the derivative of f of x. And then we want to substitute x equals 1 into that. Now I want to be really clear that you cannot write this, because that would be the derivative of f at 1. So that means you would have substituted 1 into your equation. So your equation now has no x's in it at all. Your equation is now a number. And then you calculate the derivative of that, that will be 0. So you're not calculating the derivative of f of 1. You need to calculate the derivative of f of x. Then you substitute 1 into that, given that x equals 1. Now, your CAS doesn't write that as a smaller font, so I'm going to, given that x equals 1. And then you want that to equal 4. Now, the problem is, if you then type equal 4, you've got this weird issue here where your CAS is going, hang on, what's happening here? 1 doesn't equal 4, it's all very nasty. So what you actually need is that to be equal to 4. Now, if you don't type this bracket in first, you will find it completely impossible to re-edit your expression to get that bracket back in there at the end, okay? Trust me on this. So when you enter these in, the first thing you must type is that opening bracket, okay? Then you're going to do shift minus for your derivative. With respect to x, we're differentiating f of x. Okay, outside of the derivative bracket, given that x equals 1, and then outside of that bracket, that whole thing has to equal 4. Okay, and then we want the same thing for the next one. Bracket first, derivative with respect to x of f of x outside of the derivative function. Given that x equals 0, substitute x equals 0 into that derivative, and then all of that has to be equal to 0. Okay. Alright, and so when we do that, we get our values of a, b, c, and d. So we find that a is negative 6, b is 11, and c is 0, and d is 3. Now again, be clear about what the question's asking you. This says find the values of a, b, c, and d. We've done that. If it says find the function, you would obviously put that back into the question. But yeah, making sure that you are comfortable with knowing how to enter in this expression is really important. These kind of questions will come up with context around them as well. So it's important that you can formulate this problem. But you wouldn't be expected to do this for simultaneous equations with 4 unknowns by hand. I'll screenshot that CAS screen and put it in here later so you can refer to the notes with the screenshot there if you need it. Okay, final example. Find the local minimum and maximum values of f of x equals da, 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 da. Okay, between there and there. Okay, so find the local minimum and maximum values. So let's be clear about what that's asking you for, right? You've got some kind of trig function here. It doesn't matter. I'm just going to draw it in. The local maximum value is the highest point on the graph. That's the maximum value of the function, okay? That's the minimum value. So when you're finding the maximum value of a function, it is the biggest value of f, the biggest y value. It's not the x value where the maximum happens. So it's really important that you're clear about answering those questions precisely. All right, so we want local maximum and minimum values of this trig function. So derivative is going to be, so we're going to have cos 2x plus sin 2x. So it's not just a simple trig function. Again, the graph's a bit hard here. You would need to think about addition of ordinates to draw this graph. So let's use our calculus to find where those turning points are. There'll obviously be more than one here, but we've got that restricted domain, so hopefully there's just the one in that domain. Sorry, f dash x, so we're going to differentiate this. Derivative of cos 2x is negative 2 sin 2x, and derivative of sin 2x is plus 2 cos 2x. We want that to be equal to 0 to find the stationary points. Alright, let's add the sin 2x. So we've got 2 cos 2x equals 2 sin 2x. Divide by 2. And then we can make a tan equation here because we know tan is sine divided by cos. So dividing both sides by cos will leave us with 1 on this side. And sine of 2x over cos of 2x, which means that we get 1 equals tan of 2x. Okay, so we're solving a trig equation. So tan equals 1 is pi on 4. Okay, so tan of pi on 4 is equal to 1. Tan is positive, so thinking about quadrants, it's going to be pi on 4 up here and pi on 4 down here. 2x is going to be equal to these solutions, and we want all the solutions between 0 and 2 pi. So we're going to do 2 complete laps, which means our first solution is pi on 4, our next solution is 3 pi on 4, and then we have 2 pi plus pi on 4, which will be 9 pi on 4, and 3 pi minus pi on 4, which will be 11 pi on 4. And so x will be equal to pi on 8, 3 pi on 8, 9 pi on 8, and 11 pi on 8. Okay, now you can use a bit of your understanding of trig graphs here. A trig graph won't have a stationary point of inflection, so these are either going to be max or min values, and they should alternate as well. So we're going to get, pi on 8, if that's a minimum, then 9 pi on 8 should be a minimum as well. Okay, so let's substitute these values into our original function to work out the y values. So let's do f of pi on 8 is going to be cos of 2 pi on 8, which is pi on 4, plus sine of pi on 4, which is 1 on root 2 plus 1 on root 2, which is 2 on root 2. If we were to do f of 3 pi on 8, so that is cos of 2 times 6 pi on 8, which would be 3 pi on 4, plus sine of 3 pi on 4. Okay, so 3 pi on 4 is in the... sorry, I've got my solutions wrong there. My apologies. Been a while since we've done some trig. This solution around here is pi plus pi on 4, that's 5 pi on 4. And so the second solution, my apologies, is 13 pi on 4. Okay, sorry, so this should be, and so therefore my final solutions here are 5 pi on 8 and 13 pi on 8. Sorry, it's getting a bit squishy here. I'm trying to write small because I haven't left us enough space again. So when x is 5 pi on 8, we'll have back in our original function, so we're now looking at f of 5 pi on 8. 2 times 5 pi on 8 is 10 pi on 8, or 5 pi on 4. So cos of 5 pi on 4 plus sine of 5 pi on 4. So 5 pi on 4 is round here in the third quadrant, where both cos and sine are negative. So that's negative 1 on root 2 minus 1 on root 2. And so that's minus 2 on root 2. Now, if we were to think about the next pair of solutions, we should get the same thing happening. So f of 9 pi on 8 is cos of 9 pi on 4 plus sine of 9 pi on 4. And quite literally, 9 pi on 4 is in the same position as pi on 4. So you're getting exactly the same solution. This will also be 2 on root 2, and you'll find the same thing happens with 13 pi on 8. You'll be looking at sine of 13 pi on 4 and cos of 13 pi on 4, and they are around here. So it's exactly the same as the solutions for 5 pi on 4. So this should be negative 2 on root 2. So we've actually seen 2 complete repetitions of this graph. This graph actually only has a period of pi, so we actually really only needed to do 0 to pi to find the local minimum and maximum values, because the same thing repeats in the next period. Okay. All right. So again, putting the information I've got here together with my understanding of the trig functions. If that's a stationary point, it's either a local maximum or a local minimum, and so therefore the bigger y value is going to be a local maximum. The smaller y value is going to be a local minimum, given that I know this function type can't have a point of inflection. Okay. If you're not sure though, using your sign diagram to calculate values of the derivative between these 2 points and to justify your values. So we've got maximum value of f is equal to positive 2 on root 2, or that might be written as, if we rationalise that, it's going to be 2 root 2 on 2, so that's actually root 2. And therefore, minimum value of f is negative 2 on root 2, which is negative root 2. Okay. And so there's our solution. Okay, finding our stationary points using our CAS, it's just about solving derivative equal to 0. There is also, obviously in the graph, you can use minimum and maximum but on the graphing screen, but you'll only get decimal values. So algebraically solving your derivative equal to 0. There is also something called function min and function max. Let me just illustrate that over here on the CAS before we finish up this video. Okay, so if I wanted to find the minimum and maximum values of this function, I can define my function first, perhaps to help me. So I'm going to do this example 5. So if we define f of x equal to cos 2x plus sine 2x, making sure my CAS is in radians, otherwise it won't differentiate correctly. Cos 2x sine 2x. So function min and function max are in the calculus menu, so menu 4. So you can use your derivatives, they're there, but we can also use function minimum. So if we want function minimum of f of x, and we need to put comma x as well for function minimum, it will give you the x value where f of x is a minimum. And I think in this instance, let me just see, we're going to need, yep, because it's a circular function, there's infinitely many x values where we have a minimum. So we're going to need a restriction. So we can put our restriction from 0 to 2 pi. I'm actually just going to put it from 0 to pi, because otherwise I'll get the two solutions because I've got two periods. So we only need to look over one period. The same thing will happen again in the next period. So period here is from 0 to pi. So the function minimum happens at 5 pi over 8. So again, it doesn't give you the minimum value of the function, it gives you the x value where the minimum value happens. And so obviously to find that minimum value, f of 5 pi on 8 is negative root 2. Function maximum, so menu 4(8) for function maximum. We want maximum of f of x at it, the x value that gives maximum. Given that 0 is less than or equal to x, which is less than or equal to pi. So function maximum happens when x equals pi on 8, and then obviously substituting pi on 8 into your function to find what that maximum value is, which is positive root 2. Okay, so you can use function min and function max. Alternatively, derivative of your function, solving the derivative of f of x equal to 0 over the first period of a periodic function. So when x is between 0 and pi. Comma x in my solve function. I get my two solutions, and again, f of pi on 8, f of 5 pi on 8 to find the y values. Obviously, if you wanted to complete a sign diagram, you could also then use your CAS to help you calculate the value of the derivative at the points between the stationary points to justify the nature of them. Okay, plenty of work to do here, just practicing finding coordinates of stationary points on a variety of functions. Obviously different ways the questions can be phrased as well. So again, lots of important algebra and practice to be doing here. So I want you to do these mostly by hand, unless it's a question like this one here where you're going to end up with 4 equations with 4 unknowns. But for now, mostly by hand. Once we get into the more worded application problems, we'll work more with the CAS.